Okay, we retain another integral. You've got the integral from 0 to infinity of x to the 2024 over x squared plus 1 times x to the 2024 plus 1 dx. Okay, not too far back, I did the integral of just 1 over x to the 2024 plus 1. I think this case is quite a bit different, so definitely a different method. I'm not sure if there's other ways to do this, but what I'm going to do is let's just try a trig substitution on this. Noticing where we have x squared plus 1, it seems like the substitution for tangent's going to work well here. So doing this, take a derivative. For dx, we have just secant squared t dt. And I think let's get a value for t while we're at it. So if I take arctan on both sides, we can isolate t, and we have t is just arctan of x. So go ahead and substitute what's going to happen when you plug infinity in all the way over here. Arctan of infinity is just pi over 2. Then for 0, arctan at 0 is just 0. X 2024, this is going to become tangent 2024 of t. Then I'm going to simplify this quick. Like for x squared plus 1, we can use the identity that this is going to be the same thing. X squared plus 1 is going to be tan squared plus 1. But tan squared plus 1 is just secant squared. So for this piece, we have secant squared t. This is going to be the same as this with a plus 1. So we have tan 2024 t plus 1. And then dx is this stuff, secant squared t dt. But then secant squareds are going to cancel. And then here, we could probably leave it, but I like to do this. Let's multiply in, because tan's going to be sine over cosine. If I multiply in cosine 2024 in the numerator and denominator, I think that's going to clean it up a little bit. So distributing this in and cleaning it up, what's going to happen? We're going from 0 to pi over 2. The cosine's going to cancel, and this is going to become sine 2024 of t in the numerator. But then this term is going to work the same way. This is going to be sine 2024 t. Cosine times plus 1, that's going to become a plus cosine 2024 t. And now at this point, you might recognize this. Some of you might already know the answer, because this is kind of a common setup where you could kind of just do like a formula and go right to the answer here. But I'm going to do it out just so we can see how it works a little bit. So what I'm going to do is let's use King's principle on this. With King's principle, what's going to happen is our bounds are going to stay the same, but what we're going to want to plug in for t, for if this whole thing here is our f of t, what we want to plug into it is a plus b minus t, so that's going to be f of pi over 2 minus t. Now, when you do this, we only have two things to deal with. We've got sine or cosine. Let's not worry about the exponents for the moment. So sine pi over 2 minus t, complementary angle formula, that's cosine of t. And then same kind of thing here. This just turns sines to cosines, cosines to sines. And so this is going to be sine of t. So putting the exponents back on it for sine, when we take this to the 2024 and take this to the 2024, we're going to get cosine 2024t, sine 2024t. So doing it out in the numerator, this is going to transform to cosine 2024t. And then notice the denominator is going to stay exactly the same. We're going to change the order, but the order doesn't matter. We'll just put it back. And using this, we're going to have sine 2024t plus cosine 2024t. But now from here, let's just go back and let's label the integral. This whole thing that we want is going to be I. And so then this is I, and this is also I. So what I can do is just add these two together. So when we do that, we're going to have two copies of our integral, 2i. We have the same bounds, right? We're going from 0 to pi over 2, same denominator, so we can just write that in. But then adding the numerators up, this one and this one, what we're going to get is exactly the same as the denominator. Cancel everything off, we're just integrating 1. Let's get rid of this 2 because we're solving, our goal is I. So if we divide by 2 here, multiply by a half here, now we've isolated our solution. Integrating 1, we got 1/2. Integral, that's just going to be t evaluated from 0 to pi over 2. Plug in pi over 2 for my final solution of this, we just get pi over 4. And now a couple notes on this. Like I was saying back here, you can go to an answer because it's actually just half of this upper bound when you're going from 0 to something. So half of pi over 2, pi over 4, that's the 1 second way. This works whenever you have sines and cosines and they all need to have the same exponent. So it can be this case or this case, of course, was their equivalent. But notice you also could have done it from here. Half of pi over 2 is pi over 4. The only reason I don't do it that way sometimes is because a lot of people don't know the complementary angle formula for tangent. The sine and cosine formula is more well known, but if you know that formula, you could just do it from there. And one other interesting thing on this, if you actually didn't have this in the numerator, you'll have to double check me on this, tell me if I'm wrong, but I think if that's just a 1, it still works the same way and you get pi over 4, which is kind of interesting. I guess just because, I guess it's kind of just because of the symmetry, but yeah, I think this is also just pi over 4. Okay, there you go. That's it for today. Thanks everyone for watching. Have a good day.